Enda Nicholl here. I'm the marketing manager for magnetic sensors at Analog Devices. And I want to introduce to you today the world's first single-turn or multi-turn position sensor. It's called the ADMT4000. The ADMT4000 is set to revolutionize the design of actuators and encoders globally. It's basically, as I mentioned, the world's first multi-turn sensor in a single IC. It has a very unique multi-turn technology that ADI have developed. So it can track the motion of turns without any electrical power or any mechanical contact. It also can eliminate then in current solutions in the marketplace like batteries and weakened wire solutions and so on. There's gearing with single turn sensors out there as well. So it's basically revolutionizing the design of the actuator, making it much smaller, more compact, and lower cost for our end customers. If I were to take a step back and go into Google and look for an angle sensor today or in the marketplace, there are many types out there. They can be magnetic based, they can be Hall based, sensitive to field intensity changes of a magnetic field, or they can be based on magnetoresistive technology, the XMR family, could be AMR, GMR, or TMR. These are sensitive to directional changes in magnetic field, as opposed to Hall, which is sensitive to intensity changes. There's also resolvers out there. There's also inductive sensors, and in the industrial space in particular, there's a lot of optical encoders. But you'll see that all of these sensors have an absolute measurement range of 1 turn or less. The exception would be AMR, which is a 180-degree measurement range. So that the ADMT4000 was introduced to the market back at the end of last year, and we have basically expanded the measurement range of an absolute position sensor from 360 degrees to over 6,500 degrees, or 46 turns, 16,500, 46 turns. So as you can see, it's a massive leap in technology and advancement, a capability that hasn't existed to this point. So it's very new for designers out there that actually don't realize it exists. A lot of them don't believe it works until they see it. But yeah, that's the major advantage here. So how do you solve a multi-turn challenge today? What's available on the marketplace? What has been available on the marketplace before the ADMT4000 came to the market? So customers would have had to introduce a gear reduction mechanism in combination with single-turn sensors to reduce the multi-turn count down to a single turn so it could be inferred using a single-turn sensor. But naturally, that's a very bulky, cumbersome solution. It adds mechanical wear, mechanical hysteresis. It also you still require a single-turn sensor. So that's not, it is a cumbersome, bulky solution that customers are trying to get rid of. The other option, of course, is to put a backup battery into your system and have a memory chip to retain the information when power is lost. Again, not overly desirable in a lot of systems. You don't want to have to worry about putting batteries in there and have the maintenance associated with having batteries in the system. You still need a single-turn sensor and you still need memory to create the functionality. So again, not ideal. Also, weakened wire solutions are out there as well, using an energy harvesting technique. But with the single-turn sensor, you still need then this weakened sensor, and you need an FRAM chip and so on. So it's not a simple solution, and there are some robustness concerns with that as well. It needs a lot of shielding and so on. So the ADMT4000, as you can see in comparison, is a single chip which takes care of all that other, as a very attractive alternative to what's out there at the moment. The sensor itself, as I said, released last October to the market. It incorporates 3 die. There's 2 sensor die in there. There's one AMR angle sensor in there to give precise angle measurement. There's a GMR spiral, and I'll talk about the details of that in a few minutes, which gives you the multi-turn capability. Okay, so the 360 information is received from a quadrant sensor on the GMR die in combination with the AMR angle sensor. And we have the GMR spiral then to give us the 46 turns. So all those inputs are muxed into an ADC, and we do some signal processing. We do on-chip calibration. We take out mechanical error or magnetic issues with the magnetic field on chip. we can calibrate all that out, and we have a SPI output then to provide the 0 to 46 turn absolute position information. Okay. The part is released in a 24 lead TSOP, but we will be sampling a 5x5 LFCSP in the near future as well for customers which have very tight space constraints in their application. So how does this technology work? So it's based on an effect known as shape anisotropy, and it's basically magnetic right electrical read. So the energy the energy comes from a rotating magnet in front of the sensor. So we have two structures in the core of this. There's a domain wall generator and a very narrow nanowire track. The domain wall generator has what we call a low shape anisotropy. That means that when you rotate a magnet in front of that structure, the magnetization follows the direction of the rotating magnet, as you can see from the arrows. However, the very narrow nanowire that exits the domain wall generator, that can only be magnetized in two directions, either parallel or anti-parallel, because of the physical geometry of it. It's nanometers wide. Okay, so we build that structure onto a GMR process. So any changes then in the direction of the magnetic field is picked up by the GMR stack. So we see then a resistance change in that leg, in that narrow nanowire, as the magnetization direction changes. Then on the far right-hand side, you'll see that we have created then a 46-turn spiral. We have 23 turns going clockwise, going from inside out, and another 23 turns going clockwise, still going from the outside in. So that's the design of the 46-turn spiral that's built into the ADMT4000. Again, just maybe to go into another level of detail on the shape anisotropy. As I mentioned, the domain wall generator has low shape anisotropy. The very narrow nanowire has high shape anisotropy. So, you see on the right-hand side, the rotation of the magnetic field. As the magnet rotates, you can see a domain wall starting to generate and form at the start of the nanowire track. It's not until the magnetization goes through a 180-degree rotation that flips and the domain wall goes through that leg of the spiral and changes the magnetization direction. Maybe the easiest way to explain this is using a two-turn example. Here we have the brown center here is the domain wall generator. We have the very narrow nanowire tracks exiting it. The solid arrow in the center is the direction of the magnetic field. In this case, it's going in a clockwise direction. And the blue indicates low resistance and the red indicates high resistance. And you'll see numbers there 1 to 4. They're our tap-in points. So we connect these points back to the ASIC so we can read back the new resistance when the chip is powered up. So if I rotate the magnet 90 degrees, nothing has happened at this point. If I go another 90 degrees, the first domain wall now is moved out of the spiral and it's at the ground position. If I move it another 90 degrees, you can see the domain wall now has shifted to the 0-1 position. And on the graph in the bottom right, you can see that there's been a jump in resistance or voltage. As a result of that, if I continue rotating the magnet, I'm now at VDD, a new domain wall has entered the spiral now at ground. There's been another jump in the 0-1 resistance. That's tracked. So that will be read back by the ASIC when you power it up. This is all done magnetically through the rotating magnet. So we electrically read back in the new position when we power the chip back up. So if I continue that process, I continue filling the spiral with domain walls and changing the resistance of the different nanowire legs of the spiral track. And when I power back the ASIC, then I can read back that new position, accurate to 90 degrees, and so on. And the process is reversible. If I go backwards, I empty the spiral, and it counts in both clockwise and counterclockwise directions. So I'll just bring this to the end. So what are the applications for this type of sensor? So one of the most popular would be a rotary to linear actuator, where the sensor basically would be used to replace a linear transducer in a typical rotary linear actuator application. At the moment, you would need a linear transducer or linear position sensor to track the position of that block if you want to retain that information during power down, or you want to track motion when the system is powered down. So what we would do is we put the ADMT4000 here at the end of the motor shaft. It can act as a motor commutation sensor because it has an angle sensor on chip as well as the multi-turn chip. But because if you know that the pitch of the lead screw, you can track the multi-turn position of the lead screw, and on power up then you'll know the exact position of that block. So you do not need a linear transducer in your actuator. So you can appreciate that our end users are very happy with that. They can reduce the mechanical size of their system and reduce their overall solution complexity and cost. Similarly, in a rotary actuator system, there could be typically a gear reduction mechanism involved to get higher torque. So again, you would have a motor commutation sensor at the end of the shaft, typically doing the commutation of the motor. But how do you get your position of your output shaft? Naturally, you would have to put a single turn sensor there to get that position today. Or, of course, you could add a memory and battery, as we talked about earlier, or we could add the Wiegand wire solution as well. But here, the simplest approach, of course, is to use the ADMT4000, remove all the alternatives, and you can do both motor commutation and you have your absolute position information, so you know your output angle based on the number of turns on the input side. Similar advantages here. It makes the whole system less complicated, less bulky, and it reduces the overall system costs for our end user. So some of the end applications that these actuators go into would be the robot, cobot, humanoid space. We're getting a lot of interest in those applications for it. You know, it eliminates the whole need to rehome the actuators and power up. So you know exactly where every limb of a humanoid is when you power it up. You don't need to do rehoming, or you don't need to build in backup batteries or complicated gears or linear transducers into your system. So it brings a serious amount of advantages in that application space. So there's a lot of like wire draw encoders, lifts, hoists, all those type of applications there where you can get your linear position from the multi-turn chip at the end of the rotating axis. So there's a lot of applications that we're basically coming across every day of the week. Even in the automotive space, we're actually working with a partner, building it into a seatbelt retractor, making the system intelligent, so that when you get into your car, you typically put your seatbelt on before you put the key in the ignition. So the ADMT4000 tracks the number of turns of the seatbelt spool, so that when you power on your car, it knows the extension of the belt, and so you can classify the occupant, and then that can determine the airbag deployment strategy. So you're getting more intelligence from a seatbelt system based on using the ADMT4000 than you can do today. Another emerging application in automotive is steer-by-wire, linked to autonomous driving. Here, where you're going to remove the mechanical coupling between the steering wheel and the wheelbase, you no longer can rely on the steering angle sensor to give you the wheel angle information. So you need to put in a sensor down at the wheelbase that will always keep the information on the wheel angle. When you power up the car, it's important that the wheels are pointing in the right direction, otherwise the car will go off and could cause a serious accident. So the ways that would be solved today without our sensor would be to put a linear transducer into the rack, or to put a backup battery, use the backup battery with a low power type of configuration, or put in gearing to reduce the number of turns of the motor down to a single turn. Again, here the obvious answer again is the ADMT4000 at the end of the motor shaft, doing both the motor commutation and providing the steering angle, or the wheel angle information, I should say, at the wheelbase. So some customers are concerned about the sensor's robustness. So the magnetic effect here works within a magnetic window of between 16 and 31 millitesla. So if you have a very noisy environment, we would recommend that the system is shielded. So ADI have developed a sort of a reference design magnet with shield to get our customers started if it is a very harsh environment. This has been tested up to plus or minus 5 millitesla. It will be available shortly from our website to purchase. And finally, how do you reset the sensor? So there are a number of ways it can be reset. You can reset it by overturning. If the sensor has been exposed to magnets during assembly or during transportation, we would recommend that it be reset. And it's also typically part of the process when you put the sensor into the end application to reset it. So there's different ways you can do that. You can embed a coil on your PCB underneath the sensor, which will be energized once at final assembly to set the part to max turn count. So what's happening there is the magnetic domains that move around the spiral. It all happens if you go above 55 millitesla. Basically, you're going to reset the part to max turn count. And that's what that coil does. You can also do it with another external magnet in the system, or you can simply do it by overturning the sensor. Just make sure you turn it 46 times or more at the start, and then you're guaranteed that any corruption in the spiral would be removed, and you have a max turn count reset start position. Okay, so if you want more information on the ADMT4000, we have all the collateral available on our website, data sheets. You can order eval boards, samples, and so on and so forth. So that's all there. As I said, the part released back in October of last year. We are working on next generation parts to increase the turn count as well. So if you want more information on that, feel free to reach out to me or any of our team members at the analog stand or through email afterwards. So that's it. Thanks for your attention. Questions? I'm not sure if this is a forum here for questions, but if you do want to talk to me afterwards, you can please visit our booth at 1034, and we also have the multi-turn sensor on demonstration there if you want to see a live demonstration. And I'm not telling lies here. It does actually work, guys. Okay, thank you.